Hey guys, in this video we're going to be taking a look at problem number 1 in your Kinematics packet. A baseball is thrown and follows the path in the diagram, so right here, and as we expect it follows a parabolic trajectory because gravity is the sole acceleration upon it, which is generally true for most, if not all, kinematics problems. It was also thrown at an initial velocity of v0, and it's thrown at an angle theta. The reason why we like to keep things in terms of g, v0, theta, instead of plugging in values like 50 degrees, 30 meters per second, and 9.8 or 10 meters per second squared for gravity, is because if we solve our equations and our problems in terms of the letters, like g, v0, theta, then we can solve any specific individual problem by just plugging into a formula that we've derived. So if we can solve, although it's harder to solve problems in just letters, it means that if we solved it for letters, we solved it for any case possible. I mean, this means that we solved the problem if the baseball were thrown on Mars, if the baseball were thrown on Jupiter, any form of any gravity. We've solved the problem on any planet in the universe, and I think that's pretty cool. So without further ado, let's get started on part A. We want to find the maximum height of the baseball, and that's this right here. And we've developed a couple equations, and since height has really nothing to do with delta x, right? Because delta x is only going to be affecting the horizontal trajectory. What we really care about is the height. So it's going to be a safe bet for me that one of the equations we're going to want to use to derive what this maximum height is going to be the familiar equation delta y equals -1/2 gt squared plus v0. Now remember, it's not just v0 here because we only care about the y component. So it's v0 sine theta times t. And again, if you're unsure where the sine theta comes from, remember, go back to trigonometry, and if this is our v0 and this is theta, then this here is v0 cosine theta, and this is v0 sine theta. Another equation that might be handy, and this is really where the trick of solving the problem comes in, is that let's think about the baseball's vertical velocity. And we know that the baseball's vertical velocity, so we'll say velocity vertical, is going to be equal to negative gt plus v0 sine theta. And if you're wondering why do I care about this equation when it seems that we only really care about some sort of height value, well, the question I would answer with is, what is the baseball's vertical velocity at this point right here? Because here, when the baseball is first thrown, the vertical velocity is positive because it's moving up, right? We can see that right here. It's moving up, 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 up. But when it gets to here, the vertical velocity for an instant, the tiniest instant, is going to be 0. The baseball will be moving neither up nor down when it's at the top of its trajectory. And then, of course, when it continues on its path, the vertical velocity will have shifted to downwards because it's traveling back towards the Earth. But for that instant, and there's only one instant in the entire trajectory. There's only one value of time for which the vertical velocity is equal to 0. And if we were able to find that value of t, we could simply plug it into our delta y equation right here, and then we would get a valid delta y. So let's do that right now. So if we set this, we're going to set here, we're going to set this equal to 0. So we get 0 equals negative gt plus v0 sine theta. And then simply now we have a little bit of algebra. And you'll notice that once the thought gets done, once you come to the realization that, oh, all I have to do is find when the vertical velocity is 0, once you come to that realization, everything else is a little bit of algebra. And hopefully that's good, because it means that we don't really have to think too much. But certainly it's always good to keep our brains alert. So then again, it's dividing by g, t. So the time that the time that the ball is here at the top of its trajectory is going to be equal to v naught times the sine of theta divided by g. So that's the time that we want. But we're not done yet, though, because although we've solved for the time at which the baseball is at its maximum height, we're not asked to find the time it's at its maximum height. We're asked to find its maximum height. So in order to do that, we're just going to plug in this value of time right into here. That's all we're going to do. We're going to plug it into this t squared and this t. So I'm going to scroll down from the picture right now so we can finish this. Actually, I'll keep these equations. There we go. And let's make this black. And now we're cooking. So we have delta y is equal to negative 1/2 g times... Actually, well, instead of writing delta y, because we're no longer writing delta y in terms of t, we're writing the maximum height in terms of the time that we just discovered. So this right here will be solving for the maximum height. Either the h max or the y max or whatever you want to call it. Either way, it's the maximum height. So it's negative 1/2 g t squared. Well, what's t squared? We know t is v naught sine theta over g. So t squared is going to be v naught sine theta over g squared. Right? That makes sense. We're just plugging in the value that we got for t into here and squaring it because t is squared here. And then we're going to add v naught sine theta again times time, which we know is v naught sine theta over g. Again, now that we've pretty much gotten rid of all the necessary conceptual thought, we just have a little bit of algebra left. So we know that h max, the maximum height, is equal to... I don't know what that was. What is that? What is going on? What's happening? Sorry about that, guys. My computer had an error because it is stupid. Anyway, where we left off, we found that the maximum height is negative 1/2 g times our solve for time, which is v naught sine theta over g, square it, plus v naught sine theta times, or again, our time, which is v naught sine theta over g. So all we have left to do is a little bit of algebra. So maximum height is negative 1/2 g times this whole quantity squared. And although it looks funky, again, it's just a number. I mean, we could consider it a variable, but I mean, essentially it's just a number because it's not, the initial velocity is not going to be changing. It's just going to be a set number. So it's going to be a number times a number divided by a number all squared, and we know how to do that from algebra. So we get v naught squared times sine squared theta all over g squared. And over here, we have, you can see the v naught sine theta is going to be multiplied by a v naught sine theta. And so that's going to be v naught squared sine squared theta all over g, which is going to be equal to negative 1/2. So right here, this g cancels out with that one of those g's. And we get negative 1/2 v naught squared sine squared theta over g. Actually, I'm going to write it as essentially negative v naught squared sine squared theta over 2j, just for simplicity's sake, because what I'm going to do over here, I'm going to put them over the same common denominator, so I'll multiply this by 2 over 2. So I get 2 v naught squared sine squared theta over 2g. Then I get, again, it's just 2 times one quantity minus another, minus one of the same quantity, and so fractions, simple fraction subtraction. It looks more complicated than it really is. Leaves us with our maximum height is going to be equal to v naught squared sine squared theta over 2g. So we did it. So going back to this picture, we proved that this maximum height, this value right here, is going to be equal to 1/2 v naught squared sine squared theta over g. or over 2g, wherever you want to put the 1/2. It's the same thing. And I think that's really cool, that out of just a couple of simple equations that we've derived, we made a more complicated equation. And so if I asked you, well, what will be the maximum height of a projectile thrown at 50 meters per second at an angle of 40 degrees as it experiences gravity of 10 meters per second squared, you could tell me in about 10 seconds or however long it took you to plug all these numbers into your calculator. I think that's really cool. So in the next video, we're going to take a look at finding the range, which is another really cool equation derivation. So see you then.